Well, hello everybody. It's a pleasure to join you today. My name's Gerhard, and I'm a professor of environmental engineering at Western University. And it's my pleasure to talk to you today about STAR, a new remediation technology that's just being developed. STAR stands for Self-Sustaining Treatment for Active Remediation. And I'll be spending the rest of the next few hours talking to you about that as part of this OSCE 657 State Remediation course. So I guess we'll get started, and I'll just take a moment to say that I'm going to speak to you today from my office. Most of the lectures in this course have been delivered in front of a live audience as well as online, but we thought it would be useful to try one lecture delivered only online, and that way we could have the opportunity to see how that works in terms of being an effective presentation. So this will be an experiment, and we'll give it a try, and you can let us know how this works for you. So here's the outline of the course. And you can see that we have, we're going to go through an introduction. There's 10 sections to the course, so to the lecture today. We're going to start with a brief introduction and then talk about smoldering signs, which is really the background science behind this technology. We're going to be talking about some column experiments that have been done and some two-dimensional experiments that we've done recently, and also some experiments on emissions. So I'm going to be talking about the science that's been done in the research lab to support the development of this technology. We then are going to talk about treatability studies, where we take soil from around the world and evaluate it for the STAR technology. We then are going to talk about some pilot tests that have been done in situ, on site, to prove it at a large scale, and also looking at the application technology as an ex situ process. Finally, we're going to be talking about some treatment of some more volatile contaminants, some other contaminants than we normally treat with STAR. And finally, we're going to talk about the role of numerical modeling. Since we've been talking in this course already about numerical modeling, I thought it would be a good idea to then talk about how numerical modeling is playing a role in the development of this technology. I'm going to be taking questions on chat, so do send a chat message. If you have a question as we go, I'll probably check the messages at the end of each section. So at the end of each of those 10 sections, I'll look to see if there's any questions. So we're going to start out at the introduction, number 1. And I just very briefly want to take the chance to introduce you to Western University in case you haven't heard of it. We're one of the larger universities in Canada. We're in the second largest city in Ontario, one of the most populous provinces in Canada, and the population of London is about 400,000 people. And here you see a photograph of Western University in the fall. We have a beautiful fall season here with all the colors on the trees. And Western has about 23,000 undergraduates altogether, and about 5,000 graduate students. So it's quite a large university, and it's a research-intensive university, so we have a very large graduate and research program here. It's very strong in that sense. And within the program, there's this group here. You'll see the symbol a lot called Restore. I'm one of the 4 co-directors of the Restore group. Restore stands for Research for Subsurface Transport and Remediation. We're a group within the Environmental Engineering Department. And as it says here, we have 4 professors and about 30 students, postdoctoral fellows, and engineering researchers, all doing research on various aspects of NAFLs in the subsurface, and also remediation technology, developing several new remediation technologies, including STAR. And we have programs that do lab work, field work, and a lot of numerical modeling as well. I wanted to introduce you to the team. I'm presenting research on behalf of a lot of people that have been working on STAR for about the last 8 years when we first came up with the idea. At the very beginning, you'll see here is Professor Jose Torrero at the University of Queensland. Jose and I worked together at University of Edinburgh about 8 years ago when we first came up with the idea of STAR. I'm an environmental engineer with expertise in remediation, and he's a combustion engineer with expertise in smoldering. And we used to joke together that he was in fire and I was in water, and we'd probably never ever get to work together. And then we came up with the idea of burning naphthalene as a remediation approach, and it's really been a partnership between the two of us ever since. And a lot of people have gotten involved to make this a reality. Dave Major at Geosyntec, Gavin Grant and Grant Scholes, both at Serum. They are the engineers that have taken the lead in commercializing the technology and bringing it to the field scale. So the field scale results you'll see for in situ and ex situ pilots were really led by those three. Dr. Christine Schweitzer and Guillermo Rain at Strathclyde and Imperial College are both collaborators with various expertise in chemical engineering and combustion modeling, and they've been really very helpful. And then there's a large team of researchers, undergraduates, graduate students, and postdocs at Western. Then you'll be seeing all of their research today. They've been doing everything from small-scale experiments, proving the concept at the bench scale, and also involved in modeling and experiments for scaling it up to the full scale. And really, we couldn't do it without this great team of people. And we've had outstanding funding from the Ontario government, NSERC, which is the Canadian national government, and also the Canadian Foundation for Innovation, that provides help with equipment for the kind of equipment we need to run these experiments. I just want to briefly speak a little bit more about industrial organic liquids, or NAPLs. I know we've been talking about them quite a bit throughout this course, but a lot of the things we've been talking about this course, we've been talking about NAPLs, but we've also been talking quite a bit about dissolved phase contaminants. As you know, the NAPLs partition into the groundwater, and a lot of treatment technologies deal with the contaminants in the groundwater. For example, we're talking about permeable reactive barriers, which of course don't treat NAPLs directly, but treat the plumes that evolve from NAPL source zones. Well, today what we're going to be talking about really is only the NAPL, because STAR is a technology that really treats the non-aqueous phase liquid itself. It does not treat the groundwater per se. So it's really targeted as a technology to go after NAPL source zones. So I just wanted to list a number of the NAPLs that we've talked about in this course. And I've listed them here from gasoline and diesel, the lighter end hydrocarbons, all the way up to chlorinated solvents, which of course we've been talking about a lot in this course, right up through crude oil, creosote, and coal tar. And I've tried to list them in approximately increasing order of recalcitrance. And by that I mean that they're more and more difficult to remediate. These compounds up here, as you know, have low density and low boiling points and low number of carbons in their hydrocarbon chain. So they're quite soluble, they're quite volatile, and therefore there's many technologies that can try and that are successful at remediating them, given appropriate circumstances in the subsurface. But as you move down this list, you get down to things like crude oil, creosote, and coal tar, which, in fact, we hardly have any remediation technologies for whatsoever. They don't dissolve, they don't volatilize, and they don't biodegrade. And so many, for example, coal tar sites today look exactly the way they did 100 years ago when they were created. There's very little difference. There's very little aging, very little remediation that happens intrinsically. So engineered remediation is essential for those kinds of sites. And up here you see a picture of a chlorinated solvent dyed with a hydrophobic dye. And here is a sample of coal tar contaminated soil that we have in our lab here at Western. So I'm going to be focusing on these very heavy, long-chain hydrocarbons that are generally resistant to treatment, because those are the ones that STAR happens to target very, very well, and I'll describe why that is as we go through this lecture. So here you see some classic examples of where we see coal tar contamination, for example. Here you see the typical black liquid that appears in excavated soil samples. Here's a sample of a core that we took at one of the sites we were working on. You can see it's completely contaminated with black, thick, gooey liquid. Test pits where you have a lot of mobile napple, for example, you see in the bottom left here. You also get coal tar contaminating sand seams. And of course, where there's surface waters, you can get coal tar sheens contaminating the surface water. So it's a black, viscous, recalcitrant liquid which shows up wherever it's been released to the subsurface. And where does that happen? Well, coal tar sites can be found in almost every industrialized city in the world. Between the late 1800s and the mid-1900s, let's say 1880 to 1950, before we had natural gas, we generated gas from coal. So coal gasification plants, or otherwise known as manufactured gas plants, they would produce coal tar as a byproduct. And it was something that really couldn't be used. And so the coal tar was usually improperly released or disposed of in ways that at the time was probably legal, but now we know was a significant problem, left us a legacy of contamination. So wherever you do a site investigation, you see that there used to be an MGP plant nearby. You can be highly suspicious of coal tar contamination in the subsurface. There's some other industries that use coal tar, creosote plants, tarring and wood distillation plants. Creosote, which is a similar product to coal tar, was used for preserving wood railway ties. So wherever they were producing railway ties, they would spray them with a wood preservative, and usually only a small percentage got on the wood and the rest of it got into the ground. And so we have similar problems. And as you see here, we have many known sites and probably equally as many unknown sites that haven't yet been discovered throughout the industrialized world. So what do we do when we discover coal tar contamination? Well, there's very little remedies available right now. First of all, excavation and disposal, dig and dump, is the standard go-to technology. As you know, there's a lot of concerns about dig and dump. It brings toxic materials to the surface. It involves a lot of truckloads, which involves a lot of emissions of CO2, a lot of energy use. It also results in accidents and deaths, as the trucks rumble back and forth from the site to the landfill. And then, of course, it doesn't really treat the material. It just deposited somewhere where we don't have to look at it anymore, but it hasn't really removed the liability. So it's not a great solution. There are other ways of dealing with coal tar sites, but there's very few options. One is to isolate the site from the rest of the world, either with caps or sheet piling or concrete walls, concrete barriers. So there, you basically isolate the site and prevent any kind of exposure to the groundwater or to the rest of the world. In some cases with a lot of mobile liquid, we might be able to use some multi-phase extraction, basically pumping out pure phase coal tar or napple. But of course that leaves a lot behind, even when it is successful. So it's not a very, it can get a lot of mass in a short amount of time, but it's not a complete solution. And the other option is some kind of thermal technique. Now, thermal relies on volatilizing the contaminants, transferring them to the air phase, and then sucking out the air phase. So the trouble is these contaminants are not very volatile, so it takes a lot of energy to try and do that. It can be done in situ, and there's several in situ technologies that are attempting to treat coal tar sites. Here you see one of the most common ex situ treatment technologies. It's a low temperature thermal desorption, where they excavate the material and put it into a reactor and heat the material and try and drive it off and then collect it from the vapor stream. Very, very energy intensive, very, very expensive. So here's an example. Probably the most famous coal tar site in Canada is in the east coast of Canada, Nova Scotia, called the Sydney Tar Ponds. As you can see, it was around 1900, it was they were a number of coke ovens that were powering the Sydney Steel Corporation, and coal tar was a byproduct of this coke combustion process. And a lot of it was improperly disposed of at the site, and there was a 10-year investigation to discover the extent of the contamination. There was an equally as long debate about how the site would be treated. And then right now we're going through a remediation process. I say remediate, but really all they're doing is they're capping and isolating the entire site and basically creating impermeable barriers to groundwater contacting the coal tar, and they're basically sealing off the site. So that's what's currently going on in sort of Canada's leading coal tar site. So given that background, let's talk about what STAR is. So it stands, as I said, for Self-Sustaining Treatment for Active Remediation. And it's a new emerging remediation technology. As I said, we've been working on for about 8 years. And it's based on the idea of smoldering combustion. And I'm going to speak quite a bit more about what smoldering combustion is, but that's the principle behind it. It's really a primary NAPL mass reduction approach. So by that I mean it's the kind of technology used as a first attempt when you first go into a site that has a lot of NAPL mass, a large significant source zone, and you would use it as a relatively inexpensive way to get a lot of NAPL mass out of the ground. It's probably not appropriate for polishing off a site and getting it down to, for example, drinking water standards for the groundwater passing through a site. So it might need to be coupled with a follow-up treatment technology, say a treatment trained, maybe bioremediation to do a polishing step. But really it's ideal for when you have a lot of contamination, obviously when it's NAPL, and when they're very heavy hydrocarbons, such as coal tar, such as creosote. And that's actually very useful because most remediation technologies are the opposite. Most of them, for example, bioremediation, let's say, are most effective on low molecular weight compounds, and also they have an upper limit of the kinds of concentrations they can treat. So below a certain amount, they're effective, but when you have too much contamination, they become ineffective. For example, it could be toxic for the organisms. And STAR is the inverse of that. It actually works better if you have more contamination, and it works better if you have more recalcitrant compounds. So it's a very nice complement to what's already existing in the sort of array of technologies available. And what's really exciting about it is this idea of being self-sustaining, and we'll talk quite a lot about that. But obviously, if a process is self-sustaining with respect to energy, then there's a lot of potential savings, not only in CO2 emissions, it makes the technology more green, but also it makes it more cost-effective. And really, cost efficiency is the bottom line when it comes to, in many cases, choosing a remediation technology for a massive site. So I've just put down here some references for you. There are some papers that are out in the literature, and there's, of course, the most recent work we've been doing, which is a lot of the field trials, the in situ and ex situ pilot trials, haven't been published yet because they're ongoing, but there's some websites here. This is the Serum's commercial website where they're developing commercial contacts for applying the technology on real sites. Here's our research website and another research website of a consortium that we belong to. They give more details on STAR, more than just what's in the papers. So let's go talk about the smoldering science, the science behind this technology. I'm just going to check to see if there's any questions. No. Great. Well, let's keep going then. So smoldering, everybody I'm sure is familiar with smoldering. If you've ever either smoked a cigarette or if you've ever lit a charcoal barbecue, then you know smoldering. Smoldering is basically one form of combustion. Probably you're all familiar with a candle or a gas stove, and those are forms of flaming combustion, and I'll talk about flaming in a moment. But they're both different types of combustion. Smoldering combustion is a type of combustion with no flame. So here's a picture of glowing red charcoal, and this is undergoing smoldering combustion right now. And what that means is that the carbon compounds in the charcoal are combining with oxygen, and they're producing as a byproduct carbon dioxide primarily, water, and energy. Those are the three main products of the exothermic reaction. So smoldering is unique in a couple ways. One is that it's flameless, and the second is that it's a surface reaction, and that means that the oxygen has to penetrate into the surface of the material for the reaction to take place in that surface. And this is quite different than flaming combustion. Flaming combustion is when the fuel gets gasified first. So it gets transferred into the gas phase, and then the oxygen mixes with the gasified fuel, and the burning happens in the gas phase. Here, the burning is actually happening in the solid phase, as oxygen penetrates into that solid. Because you need to have oxygen penetration, and the burning is happening in the material itself, the solid material, then it's necessary to have a porous material. So you can't have smoldering if you have something that's completely solid. So, for example, let me think of an example. If you had, charcoal in this case with no pores in it, if it wasn't a porous material, you would not get a high surface area, and you would not be able to have that oxygen diffuse into that surface through the pore network. And for example, so with coal tar, if you had a jar of coal tar, it would never smolder because there's no porous matrix there. So tobacco and also charcoal are all porous materials, and so the diffusion can flow through that porous material and penetrate into the surface. One thing about smoldering is it's an oxygen-limited reaction. Because it's diffusion-controlled, the air flows into the porous material and it diffuses into the surface. Because it's diffusion-controlled, it is necessarily an oxygen-limited reaction. And everybody knows that if you blow on glowing red charcoal, it will glow brighter. It will burn faster. And that shows you that it's being limited by the rate that you can deliver oxygen. The other thing you know about it is that it's self-sustaining. That, for example, with a barbecue, you can apply a little bit of energy for a short amount of time, maybe 5-10 minutes, 15 minutes, and then you can put the lid on the barbecue, the flame will go out, and you can walk away, and you can come back a few hours later, and all the charcoal will be gone. And that's because the process is self-sustaining. The material, the charcoal that starts to glow initially might be, if you had a large container of charcoal, the burning might just happen locally in one area. But, of course, it'll generate enough energy through its exothermic reaction to propagate the reaction to the next bit of charcoal, to the next bit of charcoal, and onwards until it progresses right through the charcoal bed and nothing's left. And so, really, it's using the energy of the material itself to achieve its own destruction. Okay, so that is smoldering. Now here's just a small comparison between smoldering and flaming, because it's easy to get the two confused, and we're much more familiar with flaming reaction. So if you look at the first line here, flaming is a homogeneous reaction. By that we mean that the gas and the fuel and the oxygen are in the same phase. They're both in the gas phase, and they mix homogeneously. Whereas smoldering has the fuel in the solid or the liquid phase, and the oxygen is in the gas phase. So the mixing is, that's why it's called heterogeneous, because they're not in the same phase. They don't mix as easily. You can see that we have a significant temperature difference because of these differences in the reactions. You get much, much hotter temperatures in flaming. We still get significant temperatures, 500, even up to maybe 1,000 degrees Celsius in smoldering, but nothing like you get in a flaming reaction. You can see there's a lot more energy released in kilojoules per gram of material burnt in a flaming reaction than you get in smoldering. Maybe on the order of twice or 3 times as much energy. And we also get much faster rates of propagation. So smoldering is really a creeping reaction, a very controlled, steady creeping reaction. Flaming, as you know, is much more potential for example, you could have an explosion in flaming reaction where it's impossible to have an explosion for a smoldering reaction. So that's an important point. Here you see some details on the CO to CO2 ratio. So some carbon monoxide is produced, significantly less than there is carbon dioxide. So carbon dioxide represents complete combustion. Carbon monoxide represents some incomplete combustion that's occurring. And you can see that there's a little bit more incomplete combustion occurring in a smoldering reaction. And we'll talk a little bit more about why that is. And you have a lot more heat flux, heat being generated per unit area of reaction in a flaming reaction than a smoldering reaction. Okay. So here's a little bit of what a smoldering reaction looks like. You have a porous material here. You have some air traveling into that porous material. This is what's called forward smoldering, because the air is traveling in the same direction as the front. The front is traveling. The blue here is the unburnt fuel. The gray is the burnt fuel, and we have a reaction zone, usually quite a thin reaction zone, traveling up through this porous material. Now, we represent the smoldering front here as just a thin line or a band traveling through the material, but really there's a very complex set of chemical reactions going on inside that smoldering front. And I'm just going to blow that up here for a second so you can see a lot of the things going on. First of all, you have the unburnt fuel up ahead of the front, and then because there's a reaction going on and there's air passing through the reaction, then you have some hot gas that is traveling into the unburnt fuel and is preheating it. So we have a very important preheating function going on where the fuel is heating up prior to the arrival of the reaction front. And if there's water there, that water is being boiled off because there's a boiling front of 100 degrees Celsius that precedes the reaction, which might be at somewhere like 600 to 800 degrees Celsius down here. So there's a heating and drying front, which is preheating the fuel. Then you have a thin layer of pyrolysis. That is basically a zone where the fuel is being broken down by the application of heat. And so, for example, in any kind of in situ thermal technology where they apply heat, you know, most of the in situ thermal technology is like electrical resistive heating and other kinds of six-phase heating and things where you're heating the ground continuously, resistive heating. You're basically applying heat all the time, and you're trying to achieve volatilization and pyrolysis. It's an endothermic process that requires continuous input of energy to break down molecules. Now, behind that is the front, the oxidation front. That is where the oxygen is combining with the heated fuel, the pyrolyzed fuel, and is producing energy primarily. And so the energy is basically being produced in this red layer, and it's being consumed in these two layers. And that is why smoldering is such an energy-efficient reaction. All the energy is being produced and consumed in basically within this front. So it's a very efficient energy production and consumption cycle with basically almost no energy. Well, there is no energy going in from the bottom, and there's no energy coming out the top. And assuming no energy losses out the side, it's an extremely efficient use of energy, and that's what makes it self-sustaining, and that's what makes it such an exciting technology. Behind the oxidation front is a cooling phase because you have cold air coming in and cooling down this region, and then behind that you basically have cold, inert material with basically no carbon left in it whatsoever. So that's what's happening, but it's all happening inside a very narrow band, and that band travels up through the material as a traveling front. Okay. So if we just talk in general terms about these chemical reactions, the main reactions going down, and there could be hundreds of them, but they're in two main categories. We have these pyrolysis reactions, which I mentioned was basically endothermic and involves the breakdown of the fuel into simpler components. And then we have the oxidation reaction. This char that's being formed reacts with oxygen and produces energy in CO and CO2. So here we see the two reactions, generally written out in a very simplistic manner. And here we see that, for example, peat is a material that's been studied in detail for smoldering, because as you know, whether you have a peat soil supporting a forest, if a peat smoldering fire happens, then all that peat gets wiped out and all the trees die. So it's a very serious problem. For example, in the peatlands of Scotland, where they have a lot of peat forests, if you have a smoldering fire, it can devastate the entire forest. So we've studied the smoldering of peat, and you can see here the carbon density, which increases when you go through the pyrolysis process. But then after the oxidation process, there's virtually no carbon left. It's all been generated into CO, CO2, and energy. Okay, so this is the most complicated equation I'll show. This is an analytic, and you don't need to understand this in detail, but I want you to have an appreciation for the kinds of mathematical analyses that can be done. This is a energy balance on that front, on that thin red line I showed you 2 slides ago. If you just take a frame of reference that moves with that front as it moves up through your porous medium, and you do an energy balance on that, and here you assume no heat losses to the external world, then the velocity of the front is a function basically of that energy balance. The more energy that you generate and the less energy that you lose. So the top here is energy generated, and the denominator here is energy lost. And you can see the four main components of this reaction. We've got energy coming in because you've got hot gas. Basically, you got gas passing through a hot zone. Remember, it's passed already through a zone that's been heated, so it gets some energy from that and brings it to the front. And then we have the heat of combustion here, basically generating the energy at the front and releasing energy. But at the same time, you've got a solid here that's absorbing. In this case, we've got a soil. This is the reaction equation developed for NAPO blobs embedded in soil. So we've got soil that's absorbing the energy, and we've got the NAPO also requires to be absorb some energy. And now, example for peat or for charcoal, you don't have this term. You just have the material itself that absorbs the energy, and you don't have any other term. And the details are given down here, but you get a sense that this velocity of the reaction can be controlled by a lot of variables. There's a lot of things going on in here, and so it's not a straightforward analysis. Now, I just wanted to mention that if you look into the literature about smoldering, which of course we've done, there's almost nothing about the smoldering of liquids. In fact, virtually zero. Everything that's been studied has been studied about, because you have to understand, in the history of combustion research, smoldering has always been a problem. It's never been a good thing. It's always a bad thing. So smoldering has always been studied about what could go wrong. For example, the smoldering of cushions can lead to a house fire. And the smoldering of insulation can lead to a fire in a factory. And the smoldering of spacesuits can lead to fire in a space station. So all the research on smoldering is on these kinds of materials, trying to think about how we can prevent some kind of serious fire. So you can see here all sorts of studies on, and the other thing is that they're all on solids, porous solids. And you see that many of them are done with natural convection because, for example, if you drop a cigarette onto a couch or a sofa, that reaction will happen because not that you're forcing air into the porous medium, but natural convection of air into the porous medium. So a lot of reactions are done with natural convection, a lot of the studies, and with solid materials. And for these ones that involve forced flow, I'll show you an example of what they mean. Here's an apparatus that was, here they put some insulation into a wind tunnel, basically, and they started to smolder it. They ignited it at one end, and then they blew air past it, and they call this forced airflow, but really the air is just flowing over top of the insulation, and a little bit is flowing, getting drawn into the reaction here as the reaction travels through the bed. The reason I mention this is because all of these conditions are very, very different from what's going on in STAR. And so really, when we started doing research on STAR, we really had to start from the very beginning, from square one, to understand the particular conditions about STAR. And you'll see why that is in a moment. So here's an example of the types of research that was done. Here's a type of fire, and this is one of the few areas where there's been a smoldering of a liquid. Here, where the concern was that you could have flammable liquids, which are basically heat transfer fluids, leaking out of pipes in some kind of industrial reactor and leaking into the insulation that surrounds that reactor or that thermal unit, and then catching fire. So you have a porous material here, you have a liquid embedded in it, and you can see the effects of the smoldering fire traveling through the insulation. So that's the kind of thing that has been studied previously. Okay, now how does smoldering happen for NAPLs? Well, this is our conceptual model. Here we've got a soil. Here you can see the soil grains in beige, and you can see the NAPL blobs in black that occupy this pore space, primarily the pore bodies and not the pore throats. And there can be water or air in the rest of the pore space. So we have a partially NAPL saturated porous medium here. And the idea was that, just like with the barbecue, that we would add a heating element and apply some kind of local ignition at one isolated location. And what that would do would heat up the soil, and it would heat up the NAPL blobs in a very isolated location, while the rest of the material is all basically ambient temperature. It's still cool. And then, once we reach some kind of ignition temperature for those NAPL blobs, we would start to apply air, because air is, of course, what's needed to start the exothermic combustion reaction. And by applying the air, we would combust that liquid in the pore space, and the energy would be transferred forward. Remember, I talked about forward smoldering. The energy would be transferred forward and would preheat the NAPL blobs ahead of it. Then we would turn off the heating element, but we would continue to blow the air, and this self-sustaining reaction would continue through the soil until, when there was no NAPL remaining, the reaction would shut itself down automatically. We would have soil, clean soil remaining, and the NAPL would be gone. That was the idea that we came up with about 8 years ago. And we said, let's see if we can make this happen. So the very first thing we did was we did some proof of concept experiments, and this is basically a small beaker that you can see would be on our bench top here. It's a quartz glass beaker, so we can see through to the inside. And what's inside there is an air diffuser, basically a pipe with holes in it that we can blow air into. And we have a little resistive coil. So it's basically what you would find inside an electric kettle. You apply electricity to it, and the resistance of it heats up and produces hot temperatures in the immediate vicinity of this coil. Then we have coal tar contaminated sand on top of that. Here you see really only about 5 centimeters of sand, and we have a thermocouple placed every 1 centimeter. So we can track temperature as a function of distance and time. We also, of course, video it with a camera, and we collect all the data, and that's the process, basically, for the proof of concept experiment. So I'm going to show you now is a webcam video, very simple webcam video of this process. So here's the reaction igniting at the bottom, and the heater is off, and this is a self-sustaining reaction traveling up our column. And you can see it glows, similar to the way the charcoal glows, and I'll show you that one more time. So this is going up a height of about 5 centimeters, and this is speeded up 50 times, so that probably takes on the order of something like 10 minutes to actually occur. So it's sort of a slow propagating reaction, I guess slow for combustion, but not really slow for remediation. For remediation, let's say compared to, well, pretty much any other kind of remediation, that's very fast. And here we see a chemical analysis. We see, basically this is the material before, sand, and we bought some fresh coal tar to mix with the sand. And here's the sand afterwards. It looks pretty much like the sand did before we started. We have basically no TPH, or total petroleum hydrocarbons, left, no PAH, and no volatile. There's basically nothing left. And this is very typical of what we see for the last 8 years. Basically, wherever star propagates, you basically have nothing left, and that's because simply, you know, we're getting temperatures of about 1,000 degrees Celsius, and really nothing can withstand, no hydrocarbons, no carbon material can withstand those temperatures, and so everything is gone. And really what I'm going to be talking about for the rest of the lecture today is the scale up of that technology, from that initial proof of concept at a 5 centimeter sand pack height, right up to the ex situ pilot tests and in situ pilot tests that we're doing now. And of course, partly this lecture is about STAR, but I'm hoping also that this lecture gives you some insight into what every technology needs to go through before it's accepted as a field scale technology. Every technology that you see started from some kind of idea and had to be proved in multiple stages with very careful analysis along the way before it could move to the next stage. And it had to pass certain criteria and thresholds before it could proceed to even the next stage and the next stage. And so I'm hoping this story gives you some insight into really what a long, slow, and difficult process it is for a technology to be fully accepted at the field scale. Remember, remediation is a very conservative area. Companies are not willing to try technologies that aren't proven, that they don't have confidence in. Remediation is expensive business, and it's always a money loser. It's not a money maker. So they're very cautious about what technologies they're going to use, and they want to be very confident that what they spend will be effective. The other thing I wanted to mention on this slide is that for smoldering, for STAR, there's a very important thing to understand about scale-up. And that is that these experiments that we're doing at the small scale, the bench scale, are really the absolute hardest scale at which you can do smoldering. Because, as I told you, smoldering is typically on the verge of extinction. It's an oxygen-limited reaction. And if you get too much heat loss, for example, to the outside world, it simply dies. So, at this scale, you can imagine that we're having heat losses through this outside surface. And so the surface area to volume ratio is a very important one for smoldering. If it's too high, if there's too much surface area, you have too much heat loss and the reaction goes out. But so this is a very difficult scale to smolder something, basically. But as you scale up, you can imagine in this big reactor here, which is basically a large-scale version of this little benchtop column, in this reactor here, there's very little, the surface area to volume ratio is much lower, and therefore you have much less heat loss versus heat retained in the porous medium. And for that reason, the reaction is much more robust, and we expect actually there's much less chance of extinction at the large scale than the small scale. So I'm going to show you a lot of research at the small scale, but appreciate that we expect the reaction to get more and more robust, less likely to extinguish, as we get to larger scales. So just to summarize what I've been saying, as I said, smoldering is a flameless exothermic oxidation reaction, and it absolutely requires a porous medium. And smoldering is self-sustaining, and in particular, it's very efficient at recycling the energy that's generated back into the reaction itself to permit unburnt fuel to then combust. The reaction chemistry, as I tried to point out, is very complicated. It's not fully understood. There could be hundreds of reactions going on in the smoldering of coal tar, for example, and probably we'll never know what all of those are. So it's very different than typical, let's say, designing a chemical reactor where you would, model the reactor and know all the reactions happening. Smoldering is probably just too complex for that kind of analysis. Smoldering is almost exclusively studied in the literature as a problem. This is the first time STAR is probably the first time, at least most people in the combustion literature or science area tell me this is the first time they've ever seen smoldering used as a solution for something. So that's exciting. Naples embedded in a porous medium can be destroyed by self-sustaining smoldering, as we've shown in our proof of concept experiments. And so it's very fortuitous, it's very useful that Naples happen to be embedded in a porous medium, because that is a fundamental necessity for smoldering to occur. And finally, as I mentioned, we expect smoldering to get more and more robust at the larger scales as it gets upscaled, which is good news for field applications.